everyone, welcome to our tutorial, the many faces which are not here, I guess. Okay, the many faces of multiplicity in ML. I'm Prakhar, I'm a second year PhD student from McGill. I'm co-presenting this with my co-organizer Shomik. You want to introduce yourself?
I'm Shomik, I'm a PhD student at MIT.
And we have a lot of other co-organizers who unfortunately couldn't come here, but I want to just do a quick shout out before we start because this would not have been possible without them. So let's just get started. Let's just set up our goals at first so that you all know what you're in for the next hour. We're going to talk about what is multiplicity, and we'll talk about this growing literature of multiplicity in the last 4 or 5 years in the fact community. We'll talk about implications of multiplicity specifically for fairness and explainability, two topics that I feel are very relevant to everyone here. We'll talk a bit about how you feel multiplicity should be addressed in different scenarios, and we'll discuss and try to come to a conclusion on how we should deal with multiplicity in different scenarios. And finally, we'll try to identify some open questions and future research directions. Okay, so to start, we're going to start with a very simple demo. There's a scenario where companies are trying to automate hiring. They get a lot of applications every day, every week, and they are not able to go through all of them manually. So they are doing a sort of automated filtering where some applications are filtered for manual review while the rest of them are rejected. Each of you will act as a company, and you will all train your own machine learning models, and we'll see how this hiring thing goes. So you can use this QR code to just open your Hugging Face space and train a model. If you're on your laptop, if you prefer to search, the name is Multiplicity Demo. When you get to the page, you'll be assigned a random seed, and you'll be assigned a random model. And then a model will be trained for you on a fixed data set. You'll get the accuracy of your model on the test set. You'll get gender disparity in accuracy as a fairness metric, and you'll get some individual decisions about different people in the data set. I'll give a minute for everyone to open it up. Are a few of us on the page yet? Okay, nice. So let's start with the very simple question of accuracy. How many of you got more than 75% accuracy? A lot of you. Okay, that's nice. That's nice. So most of you have good models. So most of you can actually deploy these models in the hiring processes. How many of you got over 75% accuracy but a really unfair model, like 10% disparity in accuracy across gender? Okay. Who got like a really fair model, maybe 1-2% disparity? Okay. So we can have a bunch of models which are supposedly equal accuracy. They are doing things equally well, but some of them are really fair, some of them are really unfair. Let's talk about individual decisions. So there are 4 people who got decisions. Let's start with the first person, which is Sam, I think. Who all hired Sam? Just one person? Okay. Okay. I think, like, can we do it again? I feel like there were 50% of you, like it just started slow. Okay, good, good. So almost 50% of you hired Sam. Imagine if one of you who didn't hire Sam had like this really amazing model with high accuracy, low bias scores, and you thought, you know what, I'm not gonna do hiring for a company, I'm gonna create my own company that does hiring for other people. I have this really amazing model. I'm going to just create this company that other companies can just outsource their hiring to me. And now with this one model that is being used for a lot of different companies, if you were to not hire Sam, every company would not hire Sam. So because of this arbitrariness that is present in the decisions, if one of you have a model that is really powerful, is being used by a lot of people, then that person can create this homogenization where individuals being rejected are being rejected from everywhere. So we're gonna, the example was hopefully to get you a bit intrigued about how you can have a lot of different models which have similar accuracies, but they have such different behavior in terms of fairness, in terms of individual decisions, in terms of interpretability. A lot of you would have gotten models that were logistic regression, random forest. A lot of you might have gotten models which were neural networks, and still you would have gotten similar accuracies. So it doesn't need to be a really complex model to be highly accurate. So we're going to talk more about throughout the next hour what are the technical terms that we use to describe this phenomena, how we talk about this, and go deeper into fairness implications, explainability implications, and also discuss at the end how exactly can we deal with this situation, what should companies do when they all have their own hiring models trained. Okay, so let's start with some terminology so that we are all on the same page. Rashomon set and multiplicity. Rashomon set. So Rashomon set comes from this term Rashomon effect from a movie that was released in 1950 called Rashomon. Are there any movie buffs who have seen this movie? Oh, okay, that's nice. Cool. So for all of you others here, it's a movie recommendation that you can take out of this tutorial. It's a really nice movie. It's a movie about subjectivity of human interpretation and human memory, and how you can have this same event with a lot of different interpretations from different people. More specifically, the way Rashomon effect is defined is a combination of difference of perspective and equally plausible accounts with the absence of evidence to elevate one over the other. So we have a lot of different interpretations. In terms of machine learning, we have a lot of different ways to interpret the same training data. But there is no evidence to say that one interpretation is necessarily better than the other interpretation. Rashomon effect in general has been used a lot to talk about unreliability of eyewitnesses, to talk about fluidity of truth in ethnographic studies, to talk about the subjectivity and biases in our memory and so on. But more specifically, when it comes to AI, around 2 decades ago, this guy Bremen, he came up with this thought that we see Rashomon effect even in AI, where a lot of different functions or a lot of different models tend to give the same error. So we have a lot of different ways to interpret the data, and they all usually give us the same error, and it's very difficult to understand which of this is a good model and which of this is a bad model. We call these different models Rashomon sets. So it's a set of models which all of them perform really well. But why does this happen? Why do we see all of these different interpretations of the data? To understand that, let's go back to how you usually talk about AI and ML in general. So we live in this really complex, highly nuanced world, and we want to set up an automated system, an AI model that can work in this world. Let's say we want to be able to judge loan applications and tell whether a loan application should be accepted or rejected. But before we move on from this world and start trying to create an AI model, we need to create a mathematical representation of this world. We need to have some assumptions on what are the features, what are the inputs that affect our decision. And this is the first step where we start to lose some nuance of the world, because we need to bring it down to some features that we can use to train our own model, to create our own model. For example, here I might say that the chances of someone repaying their loan depends mainly on their credit score or their annual income. It's an assumption I'm making to mathematically model the world, and obviously loses some nuance about how the world really works. Of course, this then dictates how we collect the data, because we collect exactly the features that we have designed for our model setup. So in this case, we'll collect the credit score and annual income of a lot of different people, and then we'll see whether they eventually paid the loan or not. And then that could be our training data to guide whether we can train a model that can predict loan application approval or not. As you can notice, there are already 2 steps of information loss going from the real nuanced world to this mathematical representation. And then even the mathematical representation is not really accessible to us. What we have access to is a finite amount of data, which we'll use to approximate this mathematical representation. And because of this, whenever we train an AI model using this data and bring it back to the world, we have created this information loss and ambiguity in how the decisions are being made. And the AI model has the freedom to make decisions and fill that ambiguity however it might like. So for example, you might say, well, I can create a classifier where if you have higher income, you get the loan. If you have lower income, you don't get the loan. It fits really well with the data. There are only 2 errors in here. And you might say that this is a good model. But someone might also say, actually, if you have higher credit, you get loan. If you have lower credit, you don't get loan. Again, a really good model with just 2 errors. You might also say, actually, it's the combination of both that matters. If you have either higher credit or either you have higher income or some combination of both, you get the loan, otherwise you don't get the loan. Again, just 2 errors. And it's it's very difficult, if you can see, to figure out which of this model should you choose. This is what we call the Rashomon set. There are a lot of words that we use for it. We call it sometimes a set of competing models. We call it sometimes a set of good models. Or we call it sometimes epsilon Rashomon set or epsilon level set. And basically the idea is all different models that have similar error, that have similar loss, so it looks like they are all similar, but they are making decisions in different ways. It matters because these decisions are going to affect people downstream. It matters because the individuals who do get loan or not get loan depends on which model you choose, even though on average, they might have the same error. More formally, we define Rashomon set as given some baseline classifier, given some classifier of what we consider a good model, all the other models which have similar error to this good model is what we call the Rashomon set. There is another definition that is being used which does not rely on a baseline classifier. So it says that for every model that has certain amount of performance, we call it a part of a Rashomon set. So to put it briefly, either you might have a target model and you say anything that performs as good as this model is the Rashomon set, or you might have a threshold performance and you say anything that does better than this performance is the Rashomon set. Notice here, the models are being trained on a fixed hypothesis set. It's like I train a bunch of models from a hypothesis class, so like from neural networks or from linear models and so on. And then I'm trying to see which models matches. But there are so many decisions that are made when you actually develop a model. And all of these decisions can impact the final model you get. So although the more traditional definitions of multiplicity tend to be about a single hypothesis class and training a bunch of models on a fixed data set with fixed preprocessing, a fixed problem statement, and so on and so forth, there are more works popping up which are exploring this whole breadth of all different decisions that we make as developers and how it affects our creation of Rashomon set. To give you some grounding of how people tend to explore this Rashomon set, I'll talk about some examples of Rashomon set exploration. To be clear, this is in no way a complete list, but it will give you some idea of how people talk about Rashomon set. We are going to divide it into 2 axes. We are going to talk about whether the search is random, meaning I'm training a bunch of models and just seeing which of them are good, or whether the search is adversarial, meaning I'm targeting to find more and more good models that are different from the models that I already have. Whether the hypothesis class itself is very complex, big neural networks, or whether the hypothesis class is simple, like a linear regression or logistic regression. For example, there's something called adversarial weight perturbation, where you start with a model and then you perturb the weights in a way such that you force a slightly different model that makes different predictions. So you get a different model within the Rashomon set while making sure you're getting diverse predictions. It is complex because you don't have to retrain the model every time. You start with a model and then you can start to slowly get new models in the Rashomon set. It is an adversarial search because you're not randomly training models. You are finding targeted Rashomon set models one at a time. Another example is dropout-based exploration, where we just drop randomly some points in the neural network and you can create a bunch of different models. It's a random search because not all of them might be good models. You have to check which of them are good, which of them are bad. But it works really well for complex settings because you don't have to train a bunch of models from scratch. We have a retraining with bootstrap data. So you get different subsets of your training data and you train a bunch of models. This works with simple hypothesis class. So one thing I want to clarify here, all the methods for simple hypothesis class still work for complex hypothesis class. It's just that because of how big these models are, it's very costly to train a bunch of models. So all the techniques that we use for simple hypothesis class will be extremely costly when you transfer to complex. So that's why we have all these approximations in the complex strategy. And finally, we have methods that are very specific to different model classes. So for example, you might have a greedy search specifically for sparse decision trees. You might have a greedy search specifically for logistic regression models, and so on. So we talked a lot about what the Rashomon sets are, but I'll hand it over to Shomik to talk about why you should care about them.
Hopefully everyone can hear me. So we've talked a lot about the Rashomon set, but we haven't defined multiplicity specifically. And so here we're separating the concept of the Rashomon set of competing models from the term multiplicity, which is going to refer to conflicting predictions. And more formally, given a baseline classifier and a prediction problem basically has this predictive multiplicity effect, if there is a specific point in the training data where the model is going to disagree with another model that has equal accuracy or equal performance. And so if we go back to the example that we saw earlier, these kind of points that have been highlighted in circles have conflicting predictions based off of the model that's chosen. And so that's kind of what we call predictive multiplicity in this setting. In the literature, there's also many other forms and terms of multiplicity. So very early on, there was kind of predictive multiplicity specifically talked about in binary classification. So that's like if the prediction classes are conflicting. Then kind of there was a work that showed, okay, well, we could have predictive multiplicity in the actual prediction probabilities themselves for different training points. And so that was this here. And then also you could have this in a resource constrained setting. So if you're using these predictions to kind of do allocations with a fixed number of resources where the threshold is no longer at 50%, but like could be varying, this is kind of multiplicity in allocations. And then also kind of other forms of multiplicity in terms of how multiplicity is arising. So procedural multiplicity is a term that's talking about the different components of the model that are different and leading to these different predictions. Data set multiplicity is the idea of like multiplicity in your training data causing this predictive multiplicity problem. Multi-target multiplicity is a work that studied different target variables that you can use for your problem formulation, and that's what's leading to these multiple predictions. And finally, explanation multiplicity is talking about the phenomenon where multiplicity in your different models is causing multiplicity in explainability methods or explanations. I went through this list kind of fast, but yeah, I think it's just the literature is kind of fast moving in this space, and people have a bunch of different terms for what kind of multiplicity they care about and what they're specifically analyzing. So this is kind of a snapshot of the different terminology that's used by the literature. Cool. And yeah, so as Prakhar alluded to, there's a really growing literature about multiplicity. Like we've seen an increasing number of papers in the space, both at FACT and at other venues, and across various domains from both like the technical aspects of exploring different Rashomon sets specifically to like more downstream implications of this for explanations, for multiplicity, or sorry, for explanations, for fairness, and for other concepts that we're going to talk about shortly. Okay, so now we want to kind of transition to thinking about what does multiplicity mean for fairness specifically. And we're going to highlight 3 different fairness concerns. The first concern is kind of about conflicting outcomes. The second concern is going to be about outcome homogenization. And the third concern is going to be about group fairness. And we're going to talk about different strategies people have proposed for addressing multiplicity based off of this concern. So we're going to walk through each of these things, and hopefully this will make a little bit more sense when I come back to it at the end. The first kind of fairness concern that people have is like, hey, we have all these models in the Rashomon set. If I'm a job applicant and I'm applying for a company, based off of what model the company decides to use, I might get rejected or accepted based off of like this kind of arbitrariness in the model selection. And so in this example, you kind of, let's say there's 3 models in your Rashomon set, and 1 had accepted the candidate, but 2 had rejected them. And so this person might experience some unfairness due to what model is chosen. Kind of a strategy to address this is, again, very simple, but just to ensemble the Rashomon models. So let's say you train a bunch of models, or in this case, just 3, and you're like, okay, we're going to just take the majority vote. And so since 2 of the models in our Rashomon set rejected the candidate, we're going to just reject the candidate deterministically. And so it's worth thinking about this like more broadly in terms of when this is fair in terms of reducing variance and when this is kind of unfair, especially for people that maybe are on like the decision boundary. And like, let's say if you were to train 100 Rashomon models and 51 of them rejected the candidate, but 49 of them accepted the candidate, are you going to deterministically pick the 51 ensemble is kind of like a problem with this formulation. But in general, this might be one way to kind of combine models and move forward. And a more sophisticated technique to kind of combine models is reconciliation. And so this is from a paper that was, I think, presented this morning. And I encourage you to read it at FACT this year. And so the high-level idea kind of builds upon the multi-calibration literature and is essentially saying that if you have two models that disagree, we can kind of find these regions of disagreement and iteratively patch the models and improve them. And so in this way, we kind of end up with a better model than the two that were conflicting and iteratively patch them in that process. And so, yeah, I won't go into the details, but encourage you to check out that paper. So both ensembling and reconciliation are kind of strategies to deal with combining models and address that kind of conflicting predictions concern. Next, I'm kind of going to move to a setting where this may be undesirable. And so if we go back to like what we were talking about in the demo, in a hiring setting, let's say like a bunch of companies have decided to use the same or similar algorithm. This term is kind of called algorithmic monoculture in the literature. Maybe you're familiar with it. But it actually happens in practice. So HireVue is a company that builds resume screening products and like hiring products for companies. And it's used by 60% of the top 100 companies in the United States. All are kind of using HireVue to do some form of automation in their hiring process. And so that kind of leads to these concerns about potentially outcome homogenization in people's decisions. So for example, if you're a job applicant and you're applying to a bunch of different companies and they're all using the same or similar model under the hood, even if you were kind of like a borderline candidate, you might get systemically rejected from all of the companies that you end up applying to. And this kind of is like a moral unfairness societally like that we don't want, like AI amplifying this homogenization effect and kind of homogenizing decisions for specific individuals. So in terms of how you can potentially address this concern, let's say you were to ensemble the models, and if everyone was using the ensembled models, this job applicant would have been systemically rejected. But what if people were to randomize using the Rashomon set? So one idea is kind of, let's use some sort of structured randomization over these Rashomon models. So since all of these models are equally good, and maybe we don't have good criteria for choosing between them, we should just kind of randomize and say that this job applicant should have a 2/3 chance of being selected and a 1/3 chance of being selected and a 2/3 chance of being rejected. And there's more sophisticated ways to do this kind of randomization, but you could randomize based off of uncertainty and use other kind of properties of the Rashomon set to do this randomization. But essentially the idea is that you can do this in a way that has minimal compromise on your accuracy. Okay, so the third concern that I mentioned was group fairness. So in the group fairness space, there's this idea of less discriminatory algorithms. So that like, for example, for a given fairness metric and for a given data set, we can basically find equally accurate but less discriminatory models that improve on that fairness metric. And so if you imagine your Rashomon set of models is this circle here, and you have your empirical sample that you've sampled using some method to kind of search over this space, you might be able to find a less discriminatory algorithm that actually improves on the fairness metric quite a bit that doesn't actually compromise your accuracy at all. And so this idea has kind of been discussed in the literature last year at FACT and over the last, I guess really only in the last year, but there have been several papers in this space. But as an example here, you have two models, one on the left, one on the right, both with an overall accuracy of 80%, but one that has equal gender demographic parity, whereas on the other side, you have a very huge gender disparity in terms of the selection rates for men. And yeah, this less discriminatory algorithms idea is interesting, I think, in the literature because it's been kind of proposed as a way to kind of work with the disparate impact laws in the United States. But there have also been some recent concerns around finding these algorithms is quite difficult in practice. So if you have if you're searching over your training data to find a less discriminatory algorithm, there's been some works that show that this is not robust if you're like deploying this and suddenly your algorithm potentially is more discriminatory when you deploy it on your training data or on your testing data. And there's been, I think Emily Black has also had a paper about discriminatory hacking. So that's kind of where you can find less discriminatory algorithms on your training data, show that to some auditor or to some compliance person, and then kind of under the hood know that this algorithm is not going to be robust when you deploy it in a testing setting. So that's kind of the concern over doing this, choosing a single model in this setting. Okay, so to go back to this table, to summarize, we kind of talked about 3 different ideas. One was combining models, and that was kind of to address the concern of conflicting outcomes. The other idea was randomizing among models, and that was kind of to address this outcome homogenization concern. And the third idea was kind of using some sort of secondary criteria to choose models. So maybe choosing models based off of some fairness metrics. And so that's kind of the third concern we have there. Hopefully everyone's okay there. Okay, great. Cool. With that, I'm going to hand it back to Prakhar to talk about explainability.
Okay, so we talked a bit about how multiplicity is important for the fairness discussion. Now we'll talk about why multiplicity is important for the explainability discussion. But before we do that, I want to just have everyone on the same page and do a very quick review of what is explanation. So under this broad idea of transparency for AI models, we have the smallest thing, which is interpretability, which is this idea that we should be able to see the causal effect of how the decision is being made inside a model. And slightly broader than that is explainability, which is that we should be able to explain the decision. Sometimes that could mean seeing the decision, but sometimes that could also mean having a black box model and explaining later how that decision is being made. So for example, in our older loan application example, let's say a new person comes in with like a very low annual income and a decent credit score, and you use the decision boundary and you say, okay, this loan application was rejected, and the explanation is that it was rejected because they had lower income. So this explanation helps you understand why and how the decision is being made. The term explanation multiplicity here means if you have multiple models, which are different models in the Rashomon set, you might get the same prediction. You might get a rejection from both of these models, but the reason why you got a rejection might be different, or the explanation you get for that might be different. So the first model might say you were rejected because you had a low income. The second model might say you were rejected because it was a combination of low income and low credit score. This is important for a lot of different reasons. For example, explainability can be used to guide future development of the model. Someone might see that, oh, my explanation says that people are always accepted or rejected because of low income, so I'm going to stop measuring credit scores, stop collecting credit scores anymore. In the second case, you might feel like, no, both of these features are important, so I need to collect both of them. Similarly, these explanations are also used as recourse to tell people what to do so that they can come back and get better decisions. So in the first case, the recourse might be that you should increase your income if you want this loan. But in the second case, the recourse might be you should either increase your income or increase your credit score to get the loan. And so it gives different options to people on what to do based on what model you have selected under multiplicity. Okay, so the implication of multiplicity for explainability is, broadly speaking, very similar to the discussion that we had for fairness. Instead of multiple outcomes, we have multiple explanations across the Rashomon set, and we will still try to combine different models. When I say combine models, of course I mean try to combine their explanations to be able to somehow create an aggregate explanation that can help us understand what's happening. There is no work that we are aware of on homogenization of explanations. I hesitate to say that it cannot exist because it might, but it's something that has not been explored yet. And finally, instead of trying to find less discriminatory algorithms and the concerns of group fairness, here we care about the concerns of interpretability or simpler models. And we say that we can actually find simpler models. You can find a logistic regression with similar performance as a neural network, which will be more interpretable using multiplicity. Of course, the broader concerns are the same, but the specifics for explainability are a bit different. So I'll go through that very quickly. Explanation multiplicity, we can talk about two broad categories of explanation. The attribute-based explanations, which are essentially telling us which features are more important. We are attributing different features with their importance. And recourse or counterfactuals, in which we are saying what needs to change in the input to get a more positive or more favorable outcome. When it comes to attribution-based explanations, for example, you might have feature importance score, variable importance score, and you might have a lot of different models that give you significantly different variable importance scores. One model says that this variable is very important, the other model says this is not very important. Instead of trying to aggregate it by taking an average or taking the majority or something, one technique that has been proposed is to create variable clouds. So these clouds of the whole range of variable importance distribution and try to visualize and understand what is the range of feature importance across all the models in the Rashomon set. Another very important idea is to give the developer the choice to pick the model they want. So visualize different models. Different models might use different features to make their decision, hence the attribution-based explanations. And then the visualization can help the developer choose which model would they prefer, which are the features that they would like to use in their decision versus other features. When it comes to recourse or counterfactuals, a lot of work focuses on trying to get some kind of probabilistic guarantees of, like, for this particular distribution of inputs or for this particular data manifold, what is the level of variability that can exist, and what if I were to choose a different model, would this recourse still be validated or not validated? And there's a lot of work on trying to get these guarantees and even find explanation methods that have lower variance for the distribution that we care about when the model is being deployed. Finally, so we talked about how we can combine different models for explanations. Let's talk about how to find simpler models. There are two very interesting results in this field. One is something about the Rashomon ratio. So the Rashomon ratio is essentially the volume of the Rashomon set divided by the volume of the whole hypothesis space. In other words, it measures how many models in your whole hypothesis space can be considered good models. And the idea is that the bigger the Rashomon ratio is, the more likely it is you can find more interpretable models. Because the bigger the Rashomon ratio is, the more models they are present in the Rashomon set, and it is possible that you might find a more interpretable, simpler model in your Rashomon set. And the second work, which I personally find really interesting, is if there is noise inherent in the data set. So if we are working on a task that has some inherent noise, or some unknowability, because it's not always possible to predict the future. When there is noise in the data, there's higher variance in the loss, because the loss can change a lot based on which data points you choose. And because of this higher variance in the loss, you want models that are simpler, because more complex models tend to have higher generalization error. They tend to overfit to this noise that is present in the data and not work well on the test data. And because of that higher generalization error, the complexity of good models goes down, and in turn you get better, more interpretable models. So to put it all together, if we are working in a domain which is a bit more realistic when there is noise in the data, it is actually more likely that you'll be able to find a more interpretable, simpler model that does as well as a more complex model, and of course at the same time is interpretable, which means that you'll be able to understand how the decision is being made. Okay, with the implications of multiplicity both on fairness and explainability, we'll now move to a final discussion.
Oh, I might need your help for the Slido here.
You can maybe go to the...
Yeah, I'll do that. Okay, so kind of to recap, because I think we maybe went through it a little quickly, but we kind of talked about different fairness concerns and different explainability concerns that kind of occur under multiplicity, or actually that kind of occur in general. And what are the interventions that you would do to kind of address multiplicity. And so there's a lot of active research in this area, so kind of the things we've talked about are very kind of, I would say, preliminary approaches or preliminary proposals that people have had. And so there's not really a consensus among the multiplicity community, at least in our perspective, on what's the best way to address multiplicity, especially given that some of these options kind of directly conflict with each other. And so what kind of can guide this decision? The domain obviously has a lot of, the domain kind of is going to give you a lot of information about what you should do. And so some of the kind of like characteristics of your decision-making tasks that might be relevant are, one, is your decision kind of a factual decision? Like, are you making like a decision about whether someone has cancer? Or is it like a normative decision, like whether someone would make a good candidate for a hiring company, like to hire? And that kind of like makes a difference in terms of like whether you kind of want to explore the set of multiple models or kind of just like try and reduce the variance and choose a single model. You might have a setting that has like a single shot versus a multi-shot scenario. So like sometimes individuals have multiple opportunities to receive decisions or opportunities. Like you could apply for multiple companies to get a job, or you can apply for multiple loans. And so this kind of multiplicity kind of may have a compounding effect if it's not dealt with in the same way across different decision makers. The kind of uncertainty, like we talked about, just the noise in the data, whether there's variability for the same inputs, basically for the target variable, that kind of has an impact on the how you might want to address multiplicity. And finally, whether decision makers are evaluating individuals separately or collectively. So like, for example, in like a medical setting or in a criminal justice setting, you're kind of evaluating everyone like individually, and your decision on that individual doesn't affect other people. But in like a hiring or in a lending setting, you're kind of comparing people. And so the multiplicity might have a different effect essentially in these two domains. Okay, so with that, we're gonna have a couple of scenarios, and we're gonna have a couple of options. I think this will be fun. We'll have a Slido. And so folks are kind of going to get to decide how they would address multiplicity in these different scenarios, and then we'll show kind of the results of the poll. So I think we have time to maybe do like 4 scenarios. They'll be short. So basically, I'll explain the scenario in like 30 seconds to a minute, and then there'll be a QR code. So have your phone out, and then you can kind of just fill out your poll, and then we'll show the results. Cool. So the first one is kind of the hiring thing that we've been talking about throughout the tutorial. So a large company is planning to automate their entry-level hiring pipeline. They receive 100 applications, and the recruiters don't have time to review every application. And they're going to train a model that's selecting the top 25% of applicants every week for the manual review. And the competitors have kind of also adopted similar hiring tools in this setting. And so when developing their model, the company notices there's multiplicity, as we've been talking about. So they're kind of searching for 100 models in the Rashomon set just to explore this. And they found that like most of these models are satisfying the 80% rule in demographic parity. So they're all kind of good models from both an accuracy perspective and from a fairness perspective. So you're kind of filling this out as if you were an applicant. So imagine you're an applicant for the company. How would you prefer they address multiplicity? The first option is use an ensemble model that averages predictions. So you would prefer that the company kind of ensemble over the Rashomon set. The second option is to randomize. So like basically anyone that would be in the top 25 applicants under any of the 100 models, we should do like a randomization over those people. And so that would be the second option. And then the third option would be to use the model with the best demographic parity on race and gender. So all of them have like satisfying the 80% rule, but like we would choose the one that like has the minimum error disparity. So take like 30 seconds to fill this out, and then we'll pop up the results. Let's keep the QR code up so that they can scan it.
Then we can wait to the page.
Yeah. We're doing good. Okay.
So we both have our opinions on how things should be, but this is one of the first times we are like looking for everyone's opinions on how they feel multiplicity should be addressed. So we are sort of excited to see the results. I'll go.
Wow. How many people filled it out?
50 people, yeah.
Oh, wow.
Nice. So it seems like the most popular choice is to randomize among individuals. Does anyone want to argue for that? If you want to take a mic and why you feel like that might be a good choice?
You could also just say it, it's a small room if you don't want to go up to the mic.
Yeah.
Anyone argued for number 3 that wants to kind of advocate for that position? Yeah.
So I would argue against the other two. It's like, for me, it's the process of elimination because the prompt was, think about the individual. When you're the individual, there is an unfairness associated with the fact that you arrived in the queue now versus, I don't know, an hour from now, and then your decision would change. So there is an argument for consistency. And the only consistent strategy here is the third one, to me, and especially not the first one. So that's why I would argue against 1, 3, and then maybe 2.
That makes sense. That's a really important point for consistency. Like there needs to be a consistency in decisions. So, yeah.
There's also a paper about that at FACT this year that people should check out if they're interested. I don't know if that's your paper, but about consistency versus arbitrariness. Yeah.
Because I voted for the 1, so I can kind of answer. I think that the consistency argument, for example, is very interesting, but I think that is choosing some values over other system of values. And it's already for me a kind of multiplicity. Which institutional norm are you going to choose that is going to impose either you decide credit scoring or, like, for example, what was the other one? Salary is the one that decides. It's a social or cultural value choice that you are making. So for me, the kind of fairest choice after that is to not choose a system of value that implies more multiplicity of choice. So this is why I choose the randomized one.
Definitely, yeah.
Yeah,
it's
that's
interesting.
True. Yeah.
Okay, let's move to the...
I think it's also important to, I feel, have the single opportunity versus multiple opportunities discussion here, because it is not just a person applying to a company and that's it. It's also a person applying to a lot of different companies. And one argument that is made for randomization is that even though randomization means you might not get your job in this one company, if you are a good candidate, you'll have higher probability. So eventually you will get a lot of offers from a lot of different companies. So this multiple opportunities versus a single opportunity. Imagine if, okay, we might have a different scenario later where we'll have a similar discussion where you might not have multiple opportunities, where it could be interesting to again see what you feel about randomization.
Can we go back to the slides real quick? Yeah.
Yeah.
Some kind of probabilistic stability. Because if you apply to multiple jobs, you're going to be accepted and then never say so something strict, right?
Yeah.
That's
exactly.
only true if all the companies are randomizing, though, right? Like everyone has to choose to adopt the strategy. Yeah. Yeah, but yeah, exactly. But there are companies that I've worked with multiple large companies, and they build this hiring tool for many of them. So in theory, it could be possible. But yeah.
When you say imagine you're an applicant, am I meant to imagine I'm trying to optimize my personal chance of getting this job, or that I'm trying to optimize my chance of getting a job in a system I feel is fair, or is it up to us, or what's going on?
I think it's up to you.
Okay, so you may be getting different responses.
Definitely.
That's true.
Okay, let's move to the second. I'm going to do the third one. And then
Okay.
Yeah. So scenario 3 here is kind of the lending example we were talking about, and this is going to be about recourse. So a bank here is using an AI system to automate small loan applications. All of the loan applications kind of involve this form, and the loan decisions made in an automated manner. If they're rejected, the bank is also going to ask the system to provide recourse to the applicant. So the applicant's going to get both a decision and they're going to get some sort of explanation or recourse of like how they can improve their chances of getting the loan. So again, here, when developing the model, the bank notices explanation multiplicity. They search for 100 models, and they find that even when an applicant is rejected by them all, the recourse is going to differ. And so imagine you're someone who was rejected. How would you kind of prefer the bank is going to address multiplicity in this case in terms of what kind of recourse is provided? So I'm going to define these because I think this is a little bit less clear. When we say use the model with the easiest recourse, we mean like the recourse that the candidate can, like the feature that the candidate can improve the quickest. So like some features, like for example, your income level are much harder to improve than other features like your credit score. And so we're going to provide the recourse for like a feature that the candidate can actually like improve quickly and have a chance of reapplying and getting the loan. The second one is like the most robust recourse. So this is kind of the, in this setting, we're looking at like the providing recourse that flips the decision for more of the models in our set. So if we have like 100 models, we want to provide the applicant with some sort of recourse that's going to like increase their chances across more of these models. So potentially, if they're applying to other banks, this is also helpful for them if other banks are using kind of AI systems, potentially. And then the third one is kind of using the model with the most diverse recourse options. So this means that like the model kind of allows you to like improve in multiple dimensions. So like you could improve your income or you could improve your credit score, and both of those things would improve your chance at getting the model. Obviously like one of those models has to exist, but we're making the assumption that such a model does exist. So hopefully those three options are a little bit more clear, and go ahead and do the same thing and fill out the poll.
I think people did already. Ooh, it's a tie.
Yeah, I think this is also, for me, really hard to reason about without more information as well. Like this is a setting where like it's really tough, but yeah.
Anyone want to fight?
Anyone want to kind of has more expertise in this area and wants to, yeah. Are there any recourse people maybe in the room?
No expertise, no. But I guess my intuition on this would be that it very much depends on the applicant that we're interested in. Because really what this is, you know, what is the information that will be most helpful for getting that applicant to get approved later. And so for some people, it might be better to receive the easiest recourse first, because that's something they can start moving on and get the ball rolling. And that can help their brain more than seeing, you know, something that's very robust, but maybe very difficult. Whereas like for other people, which the people in this room seem to be more inclined toward, you know, we want to see, you know, what is everything that I can do that will most likely give me the best situation. I'll act on it however difficult it might be. So
yeah,
I think that's
really
kind of interesting.
Yeah,
yeah. So like an applicant
decision.
specific, applicant specific recourse.
Yeah.
For lack of a better term.
I actually voted the first one, but I think we can create the fourth one, right? These three are not mutually exclusive, and you can provide all of this information to user. Of course, the message is going to be longer, so the cognition effort is going to be longer, but I think it is useful for people to know everything that they can know. We don't have to make a choice here.
So one, you might have models that allow you to not have a choice, but you might also have models that force you to have a choice. So you might have a model that relies on easy features, but that model doesn't give you multiple options of recourse, but you have a different model that relies on a lot of different features. So it gives you a lot of different options, but some of those features are not easy. So the bank will make a choice, and based on the choice, the applicant might be forced to get like the easy recourse, or might be forced to get like different diverse options. So it depends on the quality of the model, but sometimes it can happen that you have to make a choice. Yeah.
let's go to the last
So I would probably prefer the model with that is not listed here. So the simple model, which allows me to see in advance whether I will get the loan or not, rather than having to have a recourse option.
Yeah, that's a very important point as well. Like having something interpretable rather than this recourse explanations. Anyone want to fight for the third one?
Oh.
Is that what you said?
No, I was saying we should do the last one.
Okay.
Yeah, let's move to the last scenario and then we'll come back to
Unless there's
discussion.
another point they want to say?
Go ahead while we're switching the slides.
Just that I think from responsible design perspective, it matters who we are protecting and who we are prioritizing. So in this case, I feel the more diverse and like historically what can like conclude to an unfair decision would be combating with a diverse set of interventions, so I would vote for that. But it's definitely context dependent, and as you mentioned.
That's true, yeah.
I wanted to do the last scenario because I think
there's one more person.
Go ahead.
Just very quickly, I wanted to say we are fortunate in the EU to have the GDPR. We give actually a right to explanation and a right to challenge this thing.
Yeah.
So same as for the last scenario, actually, I think the only option is one that provides a human operator an easy way to understand a recourse, so to interpret a model and give an explanation that can be challenged. And so something that is robust, etc., might not make sense. What might make sense is something that is easier for a human to interpret the model and provide an explanation and a recourse.
Definitely. I think that's really relevant to this scenario actually too.
Yeah.
That's why I wanted to do this one.
Okay.
But here there's like, we have a hospital now using an AI system to help doctors with a diagnosis. And so the medical records are fed to the AI system and like the doctor gets a diagnosis and an explanation. But here the doctor is the one that's studying the explanation and then is going to decide their own diagnosis, and the final diagnosis is going to be provided by the doctor. So I think some of the topics that people brought up about like the explanations being easy to digest or easy to understand are really applicable here. And so here kind of the options we've kind of put out here are one, to kind of aggregate the explanations to find the most common explanation among your different models. So let's say you have 100 models and like 70 of them had agreed on an explanation, we would provide that one to the doctor. The second option is to kind of provide all of the explanations under the sample that we've evaluated. So like if there's a bunch of explanations, we would provide them all, even if they were potentially conflicting or like contradictory in some way. And then the last option is only to provide a diagnosis if a majority of explanations are aligned, otherwise to kind of abstain from making a diagnosis or explanation and kind of just leave the decision to the doctor. And so, yeah, those are the three we've put out there. So go ahead and do the same thing and then we'll show the results.
While we're doing that, there are a few questions online. So there's a question on how is the baseline classifier chosen, which is very important to the discussion of multiplicity, of course. It's like the baseline hypothesis class. So we talked about two definitions of Rashomon set. One which was dependent on a baseline classifier, but the other which was dependent on a threshold performance rather than a baseline performance. And that is one of the motivations for why we tried the threshold as well, why people talk about threshold as well. Because, oh, I'm so sorry. Okay. Because sometimes it's difficult to talk about what and how the baseline classifier is chosen. But when it comes to literature generally, like as an answer to how the research is done right now, the baseline classifier is just any baseline model that you train, like without too much consideration for what the random seed is or what the architecture is and so on. And then you simply train that model, find a baseline accuracy, and then you try to train a bunch of models around it.
Let's do this and then we'll finish. Yeah, we only have 4 minutes here,
okay.
So I want to, yeah. I think this is really interesting. I don't know if you want to offer any thoughts on
go for it.
but I think, again, there's no perfect solution here, and like some of the thing is, it's like,
so one thing, I'm so sorry. One thing I want to add for someone who wants to defend the first one, like one thing that I find a bit is like it can get overwhelming for the doctor when you show all the explanations, and it could be like a fight between are they even going to start using it and just start ignoring it versus actually using it. So like for someone who maybe wants to defend that, the first option.
About this problem, I think a good visualization system could help. Because we are, I don't know, thinking in just showing everything together, but usually visualization systems kind of summarize in a way, and then you can explore in detail. So maybe that could help. And I think providing all the explanations would be some kind of ensemble of experts. So it would be similar to have a lot of doctors around him giving different opinions about that subject. So I think would work better for expert.
Makes sense. That's true. There can be better ways to actually give all those different explanations.
Yeah, I actually would like to counter that. Maybe for a doctor having like, in this scenario, aggregation might just mean getting like the aggregate of two opposing like interpretations, and that might just mean they go with the middle, and that might not be a very useful case for a diagnosis, especially in a critical scenario like diagnosis. Like let's say if something says, one model says that, oh, there's a chance that somebody has high risk of cancer, the other one says that, oh, there's absolutely no chance of cancer, now we are somewhere in the middle. I don't know if that's the best case scenario, but that's just...
Yeah, so there's like a chance that the information that's provided to the doctor is like contradictory in some way, and that makes it more confusing. So even a design of the system that's like, can't really account for that in a good way.
I think that sometimes this outcome diversity might actually be beneficial. So like sometimes when different models give different explanations, that might be useful. For example, the same symptoms might point to different illnesses.
Right.
And then when we give the evaluator or the doctor the multiple explanations or answer options, that might actually help.
Yeah.
Okay, we have 1 minute.
Okay, you
let's
can
go to
finish
the. I want to finish the slides, and then for people that want to leave. We just have 2 more slides. One, we wanted to leave everyone with this diagram that says we only kind of focus on fairness and explainability, but multiplicity is kind of connected to a lot of other disciplines and domains that are very relevant in the fact community, like auditing, causal inference, ethics. And so we didn't talk about all of that. There are some papers about that, and so we encourage folks to kind of keep doing more work in this space and kind of build out this connection between multiplicity and other topics. And then finally, kind of some directions for future work that we thought were interesting. I want to particularly highlight the last one because we kind of avoided any discussion of generative AI in this tutorial, and I think multiplicity in generative AI is kind of really underexplored and kind of potentially in a domain where there's only like a few large foundation models, and we've kind of all chosen to agree to use these models. We're not able to like explore the alternatives as well due to computational costs, and so there's a lot of kind of interesting topics there, especially like that kind of around the generative monoculture idea. But other topics in this space kind of that could be relevant are like prompt multiplicity, right? Like if you have multiple prompts that are giving conflicting or inconsistent outcomes, that might be a setting that kind of relates to the decision-making setting. And pluralistic alignment, especially where you're trying to find multiple models that are good for different sub-communities. Maybe these models are all kind of in some sort of Rashomon set in some way, and there's a connection there that could be interesting to explore. And with that, we want to thank everyone for attending. Thank you so much. Hopefully this was interesting to you all.
Would love to hear from you.
Yes.
Please let us know.
We have a
if you
feedback
any
form
feedback.
and a link to the slides as well. So
we have a reading list for multiplicity if you are interested. And if you want to just contact us and talk to us, like you can use this link.
Sorry we ran out of time for questions, but we're happy to kind of...
Yeah, we're happy to take it offline, or if you want to talk during the conference or send us an email or something.